Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. We're going to get started with the afternoon session. For the afternoon session, it's my great honor and pleasure to introduce Professor Azu Ozdaglar from MIT. Azu finished her bachelor's degree at Middle Eastern Technical University in Turkey. She then went on to do graduate studies at MIT, finishing in 2003. And since that time, she's been a faculty member in the Electrical Engineering and Computer Science Department at MIT. She's affiliated with the LIDS, as well as the New Institute of Data Sciences, and her research focuses on problems that arise in analysis and optimization of large-scale dynamic, multi-agent network systems, including communication networks, transportation networks, and social and economic networks. Today, this afternoon, she's going to be talking about incremental methods for additive convex cost minimization. Thank you.
Thank you very much for the invitation. It's a pleasure to be here. It's my first time at NIPS. I'm very impressed with the number of participants. And I can't resist. I'm also very impressed, especially with students giving their talks in front of this audience. So with that, as Daniel mentioned, today I'm going to talk about incremental methods for additive convex cost minimization, and in particular present some of our recent work on establishing new convergence rate results for several variations of these algorithms. And this is joint work with Mert Gürbüz-Balaban and Pablo Parillo, both from LIDS, EECS, MIT. Mert is a postdoctoral associate whom we are jointly advising with Pablo at LIDS. So I will be focusing on optimization problems with a very special structural characteristics, additive cost problems, or in other words, we're thinking about problems where the objective function is given by the sum of m component functions, fi of x, and these fi of x are real valued and convex functions. So I'm going to refer to these as additive cost optimization. And throughout the talk, I will focus on unconstrained problems, namely the decision vector x can take any value in Rn, n-dimensional Euclidean space. And these arise in several important applications. Probably this is redundant for this community, but a prominent example is statistical learning problems. Assume we have a large number of data points, xi, yi, I from 1 to m. Xi represents a feature vector, yi is a target output. And many statistical estimation problems are based on the so-called empirical risk minimization, where the goal is estimating the parameter of interest. Here I denote it by theta. Think about this as a parameter that parameterizes your model. By minimizing an objective function given as the average of a loss function over data plus some penalty on the complexity of the model, which takes the form of a norm in general. And the examples of this formulation is vast: lasso, support vector machines, many regression problems, and also classification problems. This kind of formulation, this additive cost formulation, also arises naturally when minimizing an expected value, which is sort of typical in stochastic programming. So we're thinking about minimizing over some x, expected value of a function f. W is here a random variable, which we assume it takes a large and finite number of values, in which case this is exactly that weighted average. Or you can even think about W having a more general distribution, and we're approximating the expected value by a finite average. Another important application I would like to highlight here is distributed optimization over networks. And we're thinking here about m agents situated in a network, each having its own local objective function representing his private preferences. And the goal is to optimize the sum of these local objective functions using local computations by that node, as well as communication over the network that is connecting these different agents. In all these applications, as I've been trying to highlight, the number of component functions m is large. So if you want to solve it through a standard gradient algorithm, full gradient or a subgradient step is costly. This motivates us to use incremental algorithms, which exploits their additive structure and essentially updates the vector x, the decision vector, using one component function at a time, one fi at a time, okay? And the hope is that this will have reasonable progress with cheaper incremental steps, just gradients of the component functions. And because these component functions are processed sequentially one at a time, these are also clearly well suited for problems where fi is distributed, as well as they're known sequentially over time in an online manner. An important consideration then in design of these algorithms is how to choose the order for processing component functions. F1, F2, Fm. How do I choose the order with which I will use them in my processing, this incremental processing? The immediate choice is using a deterministic order. The simplest one that comes to mind is a cyclic order that goes through these component functions in cycles in a round-robin fashion, 1, 2, 3, 1, 2, 3. Or you can think about another fixed arbitrary deterministic order in each cycle, 2, 1, 3, 2, 1, 3, 2, 1, 3. Another natural idea is to use a random order. The most popular, especially in this community, is the so-called stochastic gradient descent or stochastic gradient method. Essentially, what it does is at each iteration, it picks a component function independently and uniformly at random from the collection of functions. So you can think about this as sampling with replacement from the collection. So in each cycle, you can sample the same component function multiple times, 2, 1, 1, 3, 2, 3. And you can now also think about a without replacement version of this idea, which is at each cycle, pick a random order independently and uniformly at random from all possible permutations of 1 to m, all possible orders. Okay? And this will be like a sampling without replacement, because in each cycle, you pick an order. So you pick each component function once in each cycle. And we will refer to this as random reshuffling. You reshuffle the order randomly in each cycle. Okay? I also would like to highlight network-imposed orders, which is particularly relevant in distributed optimization applications. This is basically you have to process the component functions according to an order imposed by the underlying network structure. Namely, if your agents are situated in a ring network, then you have to process the functions as 1, 2, 3, 4, just like the cyclic case. If it's another mesh network, that has another different global order that you have to use, which is also dictated by the neighborhood relations of the agents. Another perhaps local version of implementing those orders over a network could be a random one in which the next component function is chosen randomly from all neighbors of the current component function. Okay? And that would lead to the so-called Markov randomized incremental methods. So in this talk, I will talk about first order incremental methods, meaning I will only use first order information about component functions. First, I will focus on deterministic orders, in which case the method is typically referred to as an incremental gradient method. The best known results for incremental gradient method is like square root 1 over square root k type results, where k is the number of iterations. And this was established for non-smooth convex component functions. The first thing I'm going to show you is I will assume some smoothness. And under the smoothness assumption, show that we can achieve a rate of 1 over k in distances, improving upon this 1 over square root k result. And this, using smoothness, translates into a rate of 1 over k squared in function values. And we will show that achieving this rate involves adapting your step size to strong convexity constant of the problem. So we will also discuss more robust variance that does not require such adaptation with slightly degraded performance. I will then focus on random orders, in particular random reshuffling, the idea that I talked about, picking a random order in each cycle. This is used quite often in practice, numerically observed to outperform SGD, but there's no analytical results establishing its convergence rate. Using our deterministic IG results, I will show a rate of 1 over k to the 2s, where s lies between 1/2 to 1. So this is arbitrarily close to 1 over k squared. In fact, you can also achieve 1 over k squared rate with probability 1 in function values for this method. And this improves upon the existing 1 over k min-max rate of SGD. And I will show you how to achieve this rate. Basically, we will choose a particular step size function and properly average the iterates. And then finally, I will present another idea. I will go back to deterministic IG and ask the question, can I accelerate this? And we will study an interesting variant, incremental aggregate gradient, and show that it achieves a linear convergence rate. So my goal here is basically to give an overview of these different methods, highlight important features of the convergence mechanism, and hopefully also give you some fundamental ideas and approaches for analyzing them. So hopefully I'll be able to go through my whole plan. So let me start with sort of talking about the main ideas of the incremental subgradient method. This is very similar to a gradient method, except with the key difference that at each iteration, the decision vector x is updated incrementally by taking sequential steps along subgradients of the component functions fi. Okay, so instead of the full gradient, gradient f, you do it as gradient fi at each iteration. Hence, we can view this method in terms of cycles. Each outer iteration consists of a cycle. These outer iterations will be denoted with k. And there will be cycles with m sub-iterations over I from 1 to m, whereby I update this xik along the gik, which is a subgradient of fi at xik, normalized by my step size alpha k. Okay? So you can actually... sorry, I can't point to my slides, but so basically you go from x1k, inner iterates, x2, x3, all the way xmk, xm plus 1k gets you to the next outer iterate, which is x1k plus 1. Okay? So the relation between outer iterates can be written as the last bullet here. From x1k to x1k plus 1, what you aggregate is basically the sum of these giks, and those are the individual gradients or subgradients of the component functions, which serves as an approximation to the full gradient f of xk, except that it is evaluated at outdated iterates. Instead of x1k, it's evaluated at these inner subiterates. It's a prominent algorithm that appeared with a long history, that appeared in several literatures. In AI, it has attracted a lot of attention in the 80s. It's not, I don't think it's known as the incremental method, but rather the online backpropagation algorithm for training neural networks. Another well-known example of this method is the sort of recently well-studied Kaczmar's method for solving linear systems of equations, AI prime x equals bi. And this is basically incremental gradient applied to quadratic component functions with unit step size. And the IG sub-iterations in this case basically boils down to, at each iteration, take your point x and project it to the hyperplane defined by AI prime x equals bi and vary I cyclically or using some other order. And before I provide sort of a formal convergence analysis, let me highlight the main features of the convergence mechanism. Let's think about one-dimensional quadratics as our component functions. And following Bertsekas's recent book and terminology, let me denote the interval bounded by the extreme minima as the confusion region, and the rest as the far-out region. Okay? So the far-out region basically represents the region where we are far from the global optimal solution. All individual gradients are aligned, so an incremental step points you to the right direction. And it's almost as effective as the full gradient, provided you scale the step size appropriately. Whereas in the confusion region, the individual gradients are not aligned, so one takes you this way, one takes you that way, so oscillations arise. And that necessitates adjusting the step size. So this essentially shows us that the choice of step size alpha k plays an important role in the performance of these methods. A decaying step size is essential to kill these oscillations that I was talking about, as highlighted in a beautiful paper by Luo. So you need some decaying step size, but that will lead to slower convergence. So in practice, one is also often interested in approximate solutions. So it is of interest to look at small constant step sizes. It won't get us to the optimal, but perhaps it will give us a fairly good approximate solution. And several influential papers, Solodov from 98, Nedic, Bertsekas from 2000, showed that a constant small step size ensures convergence to a neighborhood of the optimal solution. And in fact, actually, there's a peculiar, interesting form of convergence that one can also establish for quadratics, in that the sub-iterates for quadratic case do converge to different limit points around the optimum, close to the optimum. So you don't get to the optimum, but you get to a neighborhood, essentially. So as I've been highlighting, there's a large literature on gradient methods on the deterministic order. There are textbook treatments by Bertsekas, Polyak, Shor, quite a bit on convergence for differentiable problems. And the rate, best rate known, is established for non-differentiable problems to be 1 over square root k under strong convexity type conditions, as I mentioned before. So the question I would like to ask as a first step is, if I assume the functions are smooth, can I get better results? So here are the assumptions I'm going to adopt. So the first one is that functions are convex, and the sum function is strongly convex with strong convexity parameter c. Okay? So think about this as my function f, not lying above just a tangent hyperplane, but above a parabola. C is the strong convexity constant. I assume some smoothness. I assume basically that the gradients are Lipschitz. Some of the smoothness is, I also assume twice continuous differentiability. And each individual component gradients have a Lipschitz constant of Li, which translates into a Lipschitz gradient for the sum function to be L, which is the sum of the Li's. So we have Lipschitz gradientness also. And also I assume subgradient boundedness, which is basically assuming that at every point for all component functions, every subgradient, or in the smooth case, every gradient is bounded by some g. Okay? So I will adopt all these three assumptions. The third one I'm going to talk a little bit about where I can actually relax it. Toward the end of the talk, I'll be able to relax the subgradient boundedness. So how do we analyze the incremental gradient method? As I've mentioned before, it can be viewed as an approximate gradient method. Instead of the gradient, I take an approximation with the component gradients evaluated at outdated points. So as such, I can actually analyze it, similar to many analysis, as a gradient method with error. So these are, remember, the outer iterates, x1k to x1k plus 1. And instead of taking a correct gradient step, I take something with an error, ek. And ek is exactly my error between the actual gradient step and the component gradients that are evaluated at these inner iterates xik. Okay? So the analysis of this part actually is simple. Smoothness buys us a lot. Using smoothness, what I will do is replace this gradient f by some form of multidimensional mean value theorem type expression, ak times x1k minus x star, where ak is nothing but the average of the Hessians over the line segment between x1k and x star. Okay? So if I plug in this expression in the first, instead of this gradient f of x1k, I can actually get a nice iteration or recursion for the distance k. Distance k plus 1 is put an x1k minus x star over there, replace gradient f with that ak, I basically get that it's I minus alpha k ak distance plus alpha k times my error. Okay? So now, the whole point of the analysis, how do I control that error? So note that gradient is the difference between the cycle error is the difference between those gradients. Now I can use the Lipschitzness and the boundedness of the gradient to control that gradient error by a term which is given by step size L, M, G. Remember, L is the Lipschitz constant, M is the number of component functions, G is my gradient bound. So when I put things together, using also a strong convexity bound on AK, which allows me to bound it by the C, together with the bound on the error, and I'm using now, from now on, this, the step size R over K, okay? K is basically a decaying step size. I can actually get a recursion for distance that way. And to analyze that recursion, I'm going to use a very nice result from a seminal paper of Chung from stochastic approximation literature, also stated in Polyak's book, a treasure for continuous optimization. So think about UK, a sequence of real numbers, and assume that UK plus 1 is less than or equal to some constant UK plus some error term. Note that A is a positive constant there, so we get some nice contraction over there. But there is some error. But S is positive, so my error is not too bad, not too big. And what the result says is, it's a little notation heavy, but I just want to highlight the important piece, basically that UK goes to 0, and the rate of decay, which is, if you see A is greater than S, it's K to the minus S, A is less than S, it's K to the minus A. So the rate of decay is governed by the minimum of A and S. Okay? Now, for S equals 1, it's not too hard to prove this. You can actually write down the evolution of the iterates explicitly, and then you get this products of 1 minus A over K. For K large, you can actually approximate this as 1 minus 1 over K to the A. When you multiply all of these things, it's actually a 1 over K to the A. And on the other side, you have the accumulated error. You can use a similar trick or approximation for 1 minus A over K. That will be like a J over K to the A. When you do the integral approximation, you get this D over A minus 1 times 1 over K. So applying this result exactly to our previous recursion, note here that S is equal to 1. And we're going to basically need to be in the first case, S is equal to 1. I want a rate of 1 over K to the minus 1 over K. I need to make sure that this constant A is greater than 1. So I need RC is greater than 1. And when I put everything together, basically it gives me the following rate. IG method with step size R over K, if you choose R to be greater than 1 over C, gives you this rate of 1 over K. And the constant basically depends on the parameters of the problem. And important thing to notice here is the one that's highlighted in red. You have to choose your step size carefully. R has to be greater than 1 over C. So this requires knowledge of the strong convexity constant of the problem. And this is actually a very widely noted problem also in several other literatures, not just deterministic incremental gradient, but also in stochastic approximation, stochastic gradient descent literatures. And very simple examples shows that this is not just an artifact of the analysis. If you don't get R right, you can actually get very, very crappy rate. This example shows that. I'm not going to go into the details, but one-dimensional quadratics, 2 functions. Strong convexity constant of the sum is 1 over 5, which actually says from the theorem, you have to take R to be greater than 5. And suppose I didn't know that, I ignored that, and I took R to be 1. You can write down the iterations and show that actually you will get a convergence rate which is no less than 1 over K to the 1 over 5th. So this could lead to a pretty bad degradation in performance. So instead of then using this kind of step size, one thinks about, okay, how about if we do a 1 over K to the S? We don't get 1 over K step, but 1 over K to the S. Then without need for adaptation to the strong convexity constant, one can actually get rate results which are robust in the sense you don't need to adapt your step size to the parameters of the problem. And basically the rate result follows from a variation of the analysis that I've talked about before and gives you a slightly degraded rate, 1 over K to the S. S doesn't go all the way to 1, if you note. And the constants there are again similar, L, M, G, R over C. So before moving on to the random orders, I'd like to also point out one additional insight that this line of analysis buys you. So let's focus on the specialized case of quadratic functions. And instead of the cyclic order I've been talking about, let me think about an arbitrary deterministic order. And let me use also the step size R over K to the S, S taking any value between 0 and 1. So for quadratics, under very little assumptions, mild assumptions, so this is just one, which is saying strong convexity. So nothing about this gradient boundedness. One can actually shows a rate result for the distance, which is more refined compared to what I just talked about. In particular, the iteration complexity is still 1 over K to the S, so I'm not gaining on the iteration complexity. But I just want you to notice the constant, which I wrote in red there, M sigma. That is a constant that depends on the order you pick. So basically, this result shows you the effect of the order which you picked in processing these functions on the performance of your algorithm. And that M sigma is basically given there. And it's nothing but the sum of the Hessians weighted by the gradients that you have processed so far. So P sigma j is the jth Hessian that you've processed times all the gradients that you've processed up to iteration j, sub-iteration j. Okay? So it's an interesting fact that we actually get this dependence on the order. One can play with this m sigma to say what kind of insights this generates. One simple thing is to note that m sigma is bounded from above by j times the Lipschitz constant of the jth function times g less than or equal to lmg, if you assume, for instance, bound of gradient boundedness on g. Gradient boundedness with a constant equal to g. So the constant on the right-hand side, if you replace, basically takes us back to the previous estimate. But the middle one actually gives you insight. Basically, what it suggests is process the functions that has higher Lipschitz constants first. So this is sort of also in line with some of the randomized algorithms that sort of process or samples the functions according to their Lipschitz functions. So there's similar insights coming from this line of analysis. So with that, let me move on to random orders. And basically, I will focus on the two popular ones that I talked about, SGD and random reshuffling. And let me also repeat what they were. SGD is at each iteration, you pick a component function randomly, independently from the collection. And RR is at each cycle, you pick a random order independently. So RR is basically sampling without replacement. SGD is sampling with replacement from the collection. Okay? There's much empirical evidence showing RR outperforms SGD. I actually picked these figures from a paper of Boteux from 2009. It's a short, very nice paper with title, Curiously Fast Convergence of, he doesn't call it random reshuffling, but SGD type methods, but this is exactly random reshuffling. And he actually uses it on a classification problem. The figures show the evolution of the function values as k increases for SGD and random reshuffling. And clearly displays on the left, if you look at the slope, a -1. So a convergence rate of 1 over k for SGD. And on the right, random shuffle, if you just fit a line, you get a slope of -2. Indeed, curiously showing a 1 over k square rate for random reshuffling. So this has been posed as an open problem in Bertsekas, Boteux, also more recently in Recht and Ray. And both Bertsekas and Boteux basically attribute improved convergence rate of random reshuffling to the fact that it provides a more even coverage of the training set. In each cycle, you sample each component function exactly once, as opposed to SGD, which may actually do repetitions. This is sort of the intuition why it sort of leads to these better rates, but the analysis is hard because of dependencies of gradient errors in and across cycles. So before presenting the analysis for random reshuffling, let me just say briefly some of the known convergence rate results, how to achieve them so that I can actually make a better comparison between these methods. SGD, similar to IG, has a very large, actually mind-boggling literature, going back to stochastic approximation literatures, Robinson, Monroe, Kiefer, Wolfowitz. It's popular nowadays in machine learning applications because of its scalability and also robustness properties. It's an active area of research. I apologize, I'm for sure providing here an incomplete list, but writing it all would take all of my slides. So I just put some of the representative papers on achievable rates, robust variance, second order versions. More recently, this is a recent paper, Hartrecht Singer, looking at the robustness properties of SGD. So if you look at the convergence rate results on SGD, for strongly convex functions, and there are some lower bounds. It's a tricky business, lower bounds. So for stochastic convex optimization, SGD has this 1 over k min-max lower bounds established by Nemrowski-Udin, more recently by Agarwal and co-authors. And one way of achieving that in a robust way, without need for adaptation to the strong convexity constant, is the Polyak-Rupert averaging, which is choosing larger step sizes, R over k to the s, and curiously taking time averages of these iterates, of these trajectories, without changing the algorithm. And Polyak and Juditsky from 92 has a nice analysis using central limit theorem type arguments that shows that if you do this with this step size and averaged sequence, and if you look at the distance of that averaged iterates to the optimal solution x star, that distance scaled with k to the 1/2 converges in distribution to a nice normal, zero mean normal distribution. So this can be translated into a rate result for function values, 1/k rate result for function values. So under the assumptions I talked about, 1 and 2, and more technical conditions, one can actually, our recent work provides convergence rate result for random reshuffling. So let me repeat, for average stochastic gradient descent, you get a convergence rate of 1/k, or k to the 1/2, in distribution, whereas here you basically get a rate of k to the s for the distances. Sorry, I was trying to reach my slides, so I can do it from here. K to the s rate in these distances to a constant with probability 1. So this is one result that shows, I think, the advantages of random reshuffling in terms of convergence rate with respect to average stochastic gradient descent. So note that this S is between 1/2 and 1. This is in distances, so it translates into a rate of 1/k to the 2s, so close to 1/k square. Actually, I will show you, we can also get something on the order of 1/k square in a minute, in function values with probability 1. And another thing I would like to also highlight here is the constant over there, theta star. If you recall all the deterministic results, the constant that I've highlighted depends on m, the number of component functions. Here, you can actually immediately write down this theta star, an upper bound on the norm of the theta star, to be L times G. Okay? So there's really no additional m on this constant. And before I go into the analysis, I just want to show you, sort of even on simple simulations, the difference in this convergence rate is striking to see. So let's just focus on the right panel here. These are histograms for the approximation error in distances. Red one is random reshuffling. Blue is SGD. And you can show, actually, within number of iterations, which is not too high, that you can see this nice concentrations in random reshuffling and this convergence in distribution, which is sort of asymptotically normal for SGD. So I will try to highlight the how to analyze this convergence behavior. But before that, let me try to sort of, through a toy example, illustrate the difference in convergence mechanisms between the two methods. So SGD, again, what it does is samples index ik uniformly independently at each iteration k. And here, basically, I wrote it also in terms of an error, but not the cycle error, because for SGD, you're just sampling IID, so thinking things in terms of the iteration error. The gradient error is simpler. You can also do the cycle comparison in terms of cycle gradient error. It just becomes more messy. So let's focus for SGD on the iteration gradient error. And let's focus on the simplest example of two quadratics, symmetric. So one is x plus 1 square, x minus 1 square. Some function basically has an optimal solution at exactly 0. Okay? And the gradients, component gradients, differ from the actual gradient, full gradient, by +1 and -1. So if you're sampling these two functions with 1/2 probability at each iteration, your error is essentially +1, -1 with probability 1/2. Okay? Leads an expected error of 0, so it has a 0 mean error. Variance has a unit variance. Okay? So you can also show that, many typical analysis does that, the error sequence is a martingale difference sequence. So similar to Polyak-Juditsky, you can use martingale central limit theorems to show this convergence in distribution and the rate of 1/√k. So if you go to RR, random reshuffling, for the same example. So now let me write things in terms of cycle gradient error, because what RR does is at each cycle samples these orders, either 1-2 or 2-1 with probability 1/2. Okay? And if you write down this iteration, other iterations, x1k to x1k plus 1, you see that there's an error with respect to the full gradient step. And that error is actually some random error. With probability 1/2, it's the difference of gradients of F2 at 2 different points, inner iterates. And with probability 1/2, it's the difference of gradients of F1 at these inner iterates, x2k minus x1k. So now, by gradient Lipschitzness, I can actually write down or bound this error as the difference between x2k and x1k. And note that even in the inner iterates, going from x1k to x2k, I take a gradient step, x1k minus alpha gradient. And therefore, the difference is actually on the order of my step size alpha k. Okay? So the error here, the cycle error, this is, I think, the most important probably feature of the random reshuffling. Gradient error, cycle gradient error is order alpha k. Its expected value is no longer 0 as SGD, but its variance is order alpha k squared. Note I'm using a decaying step size. So this says that I have an error whose variance is decaying, and therefore I have a better and better direction of descent, which will yield faster convergence. Okay? So that's sort of one of the key points to realize when you want to analyze why is RR doing better than SGD. So it has reduced variance, but the problem is in this case, EK is not a martingale difference sequence because of the correlations. In fact, if you write down, you can write down EK or decompose it in the following form. You can write it as alpha k VK, where VK is a sequence independent over cycles, minus step size times x1k minus x star. So as you see, EK depends on the starting point x1k, which depends on the random order you picked in the previous iteration. So you get these dependencies in these EKs from cycle to cycle. But the thing to notice here is that I can decompose, and that's what the proof involves essentially. I can decompose it as alpha k VK. VK is an IID sequence independent over cycles times my step size minus alpha k times x1k minus x star. But note that if you look at our deterministic analysis is valid for all orders, meaning as long as you sample all the functions once in each cycle, that result also holds true in this case, giving you a rate of O of alpha k for x1k minus x star. So that gives me a rate of O of alpha squared. So I have an independent part plus a perturbation, which is on the order of alpha k squared. And that's what allows me to analyze this method. So how much time do I have? 10 minutes, okay. So just the next 2 slides will be a little technical. I apologize for that, but at the same time, I wanted to just show you the proof or summarize the main ideas of the proof in a couple bullet points. So I just wanted to say, be able to tell you that we can actually summarize the main ideas in a couple of steps. So the idea basically is similar to many of the analysis of these methods. You write down the evolution of the outer iterates, and this is exactly what I did in IG also. How do I go from x1k to x1k plus 1? I basically get a gradient step. It has some error times alpha k. Okay? So I will do Pollack Rupert averaging. So I will average both of these, both sides of this equation. I will do the proof for quadratics. The general case is very similar. So it's easier to see it on quadratics. So because we have quadratic functions, I can actually write down that gradient as h star, or the Hessian, times x1j minus x star. And when I replace that and take the average of both sides, I get the second equation. Okay? Let me call the left-hand side of my equation ik. This is this x1j minus x1j plus 1 times step size averaged. And the right-hand side is just the average of the previous right-hand side in the first equation. If I rearrange, what I get is, from the right-hand side, I get x1j minus x star averaged. So it's exactly my averaged sequence, x bar k minus x star. Okay? Now I have an h star, which will be an h star inverse multiplying the rest of the terms. So it will be an h star inverse ik put to the other side. And also I have here h star inverse times basically that EJ term. Sum of the EJs divided by alpha j's times alpha k bar. Okay, so basically I can write down the distance of the average iterates in terms of the sum of two terms. H star inverse times the first term, H star inverse times the second term. And the proof goes through showing the following three results. This alpha k bar, which is the average step size, this is 1 over k to the s averaged. You can show that that has a rate of 1 over k to the s. Ik has a rate of log k over k. This Ik is nothing but basically how the difference sequence, sum of the difference sequence, x1j minus x1j plus 1 evolves. And finally, probably the red part is the most interesting, Ej over alpha j. That ratio converges almost surely to this theta star that I have defined before. And I also put down sort of how these different rate results follows. Log k over k, showing that this Ik converges with rate log k over k. This is basically, you extract from this difference x1j minus x star. You use the deterministic IG results on that, and use the lots of beautiful algebra, or maybe lots of ugly algebra. Depends on who is doing it. Some people like it, some people don't. So lots of algebra, and you can establish this log k over k. The other one, which is Ej over alpha j, exactly follows from the idea I highlighted in the example. So you get your cycle gradient error, you decompose it into two terms, alpha k, vk. Vk is a sequence independent over cycles, alpha k, plus some perturbation, which is order of alpha k squared. And expected vk you can write down as the theta star. By strong law of large numbers, we have that Ej over alpha j, which is essentially my vj. It's an independent sequence. If I average it and use strong law of large numbers, it converges almost surely to its expected value. Also implying almost sure convergence of the weighted version, which is the Ej over alpha j, to the same theta star. So this analysis basically, instead of the central limit theorem type arguments for SGD, allows us to use, through this decomposition, a strong law of large numbers type argument, and gets us these rates. And if you look at the sort of blue rate results or estimates here, you have forget the log k, 1 over k here, and 1 over k to the s, showing us that indeed the rate of convergence of these distances are order 1 over k to the s. Okay? And the next thing to realize is the first term, which is the term which governs the rate of decay, 1 over k to the s, consists of terms that I can actually estimate. It's H star inverse, Hessian at the optimum, alpha k bar, which is the average of my step size, and this theta star, which is all in terms of gradients and Hessians at theta star. So if I can actually estimate that and subtract it, that's a bias, and subtract it, I can actually get a rate of 1 over k, less log k over k, but I can also get rid of that log k. Okay? And that's sort of the other idea that we are proposing here, basically. This bias term, which is all related to the properties at x star, can be estimated with an error, of course. Let's say we fix the number of cycles that we're going to run our random reshuffling. In the last cycle, we estimate this bias and subtract it. That gives us a rate of 1 over k squared in function values. And if you actually simulate this over random quadratics and look at the errors in terms of suboptimality of the function values, you see an order of magnitude difference between random reshuffling and this sort of bias removed version of the algorithm. In the last couple of minutes, let me sort of wrap up with a final idea, and that's sort of this aggregating the gradients idea. I want to go back to deterministic orders, deterministic IG now, and ask the question, can I accelerate it, but while still maintaining the savings associated with this incremental access to the component functions? So remember the problem with IG. So everything is good in the far out region, but oscillations arise in the confusion region because one component gradient gets me this way, one component gradient gets me this way. So the simple idea, very nice, is basically still compute single component gradient at any iteration, but keep in memory the last m gradients that you computed, component gradients, and using those in your memory, form an estimate or approximation to the full gradient step and move along the approximate full gradient step. And this full gradient step, because you're going to be moving closer and closer to x star, will actually estimate your full gradient better and better. And that's actually an idea beautiful idea proposed by Blatt, Hero, and Gauchman in 2007. And the method basically takes the following form. So you move your x always along the direction of a sum of the component gradients. So this is not exact, it's an approximate gradient for the full function. And what you do is at each iteration k, you go compute a new component gradient at xk, and in that memory, you replace that value with the most recently computed subgradient and keep the rest the same, still move along the sum. Okay, so that's sort of the idea. Blatt et al. Established convergence for this method, a linear rate for quadratic case. This sort of idea was also used recently in this beautiful paper by Leroux and co-authors, who studied a randomized version of this, where the index is selected uniformly at random, leading to the stochastic average gradient, and proved a linear rate for the algorithm, stochastic algorithm. There's another paper which looks at proximal extensions from last year's NIPS. This is a long proof. Uses very much the stochastic nature of the algorithm, and to our knowledge does not extend to the deterministic case. So we basically analyzed the deterministic version of this algorithm with a deterministic component order, and showed that with a constant step size you can get linear convergence. And I just want to sort of conclude by showing you a very simple proof of this result. It's actually probably less than a page. And it goes as follows. Basically, you analyze it as a gradient descent with errors again. The first relation is exactly what I've been putting since the beginning, same relation for IG. The novel step is the bounding the error, gradient error. And what you can do is basically play with the Lipschitzness and so on and so forth to bound the gradient error in terms of distances, the last 2m distances. Okay? And then you can combine all these relations, pick a Lyapunov function given by the distance, and show that this distance satisfies this last relation here. And p is less than 1, so you get a contraction there. You can get a linear rate plus a perturbation. So the nice thing to notice is, using a recent result by Faiz Mahdavi and Aytekin and Johansson, if you have a perturbation here that depends on your recent finite history, you still get a linear convergence, but at the expense of a degraded rate, not with p. But the degradation is basically determined by the size of your perturbation Q, as well as the history, duration of your history, which is given by 2m here. So that's basically the idea. And with that, let me conclude. I tried to give you sort of some ideas, rate results for 3 different methods: deterministic IG, random reshuffling, deterministic IAG. I think this is a very fertile research area. I especially like the fact that it combines ideas from several different literatures: continuous optimization, machine learning, networks, control. And it has a lot of applications in large-scale networks and data processing. So with that, let me conclude, and thank you for your patience.
If you have questions, could you make your ways to the microphone? So you commented on the difference between stochastic gradient with replacement versus a random reshuffling. Mm-hmm. If you had, say, a deterministic sequence of permutations, how would that differ from the random reshuffling?
That's a great question. So I think the thing to notice is that, sorry, I keep forgetting this, and it's intentional. There's a hole here, that's why I'm folding. The iteration complexity, 1 over k to the s, is the same for deterministic order. So as long as you sample all of these components once in each cycle, you get the same iteration complexity. What is different is that constant. In the deterministic orders, you get a constant which is very bad, because it's an upper bound on all orders, right? It accounts for the worst order that you can actually pick. So it has that m dependence and various kinds of dependencies. Whereas in the random reshuffling, what you get rid of is exactly that m. So it's actually a nice constant, which can be much smaller than the constant I provided for the deterministic orders. So very good question.
When working with practical industry problems, for example, online marketing optimization, Are there any practical ways to figure out where the smoothness assumptions and boundedness actually applies?
So that's also a very good question. I think in general, my answer is that if I look at the applications that I've cited before, so even if you don't have smoothness, it's basically only in a small number of points. So I think my answer to that would be I expect many of these things to hold in practice also because in general the problems do not have too many non-differentiabilities. But other than that, I think if you look at the analysis, it doesn't assume any kind of smoothness, then you get all kinds of very bad rate results. But I think in practice, I would expect to observe more of the smooth results that we see here.
Thank you.
Okay, let's thank Azu again for her presentation.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.